Okay, hi everyone, sorry for the delay. Today we have Dr. Antonia Praetorius here from ETH in Zurich. She's kindly offered to come over to do the second capacity seminar. Her research, her PhD research that she's just successfully completed, focused on the development of environmental fate models for engineered nanoparticles. And she's just about to start a postdoc at the University of Vienna, so she's going to talk to us today about her PhD research.
Thank you. And thank you for all of you who are interested in my work and for inviting me here to give the talk. As you can see, the title of my talk, Development of Environmental Fate Models for Engineered Nanoparticles. It's also the title of my PhD thesis, which I just finished in the Safety and Environmental Technology group at ETH Zurich. And I thought, because most of you don't know that group, probably I'll give you a very quick background of what we're doing there and what our work is focusing on. So basically it's a group that is located in the chemistry department, and the basic idea is that we look at the safety of chemical processes and chemical products as chemists, but we also have a lot of environmental scientists working in the group. And the group is quite big, so we have a lot of different subgroups. Some people are dealing with safety of chemical reactions and improving chemical processes to make them more sustainable. Another part of the group where I was working in looks more at the effect of chemical products both on humans, so we also do human exposure modeling, and on the environment. And in that part of the group we have worked mainly with environmental fate models, and those were mainly used for to model the distribution of organic pollutants, so pesticides, volatile organic chemicals, flame retardants, all sorts of things in different geographical settings and for different questions. And a lot of the work is, or some of the work has also been used to advise risk assessment and regulation. And when I started my project, the basic, so the question that we were asking ourselves was, now that engineered nanoparticles were coming more and more into the focus as potential emerging pollutants, we're wondering if we can use similar approaches that we used before for organic chemicals to predict the fate and transport of engineered nanoparticles. That was the leading question when I started my PhD, and today I will tell you more about how we went about to answering this question, and I'll give you a little background and tell you about the existing models for organic chemicals that we used before, just so we all kind of start on the same page here. And then I will talk a little bit more about fate descriptors, because as you will see, there was quite a bit of debate in the field of what is appropriate here for nanoparticles. And then I will show you the framework that we then ended up developing for ENPs, and show you some examples of modeling the fate of ENPs in different rivers that we did. So, yeah, if you have any questions, I mean, if you want, you can also interrupt me in the meantime. I'll try to keep an eye on the time so it doesn't take too long, but if you want to start a discussion before, it's also fine with me. So just a little background, because I guess not all of you are working on nanoparticles from what I know. So nanoparticles are basically can be any type of material, but in the nanometer size range. And due to this small size, the materials exhibit special properties that make them particularly interesting for all sorts of different types of applications. And we find them really in many, many areas. We can find them in personal care products, in sunscreens, for example. We find them in coatings and paints, in different types of materials, sports equipment, electronic equipment. So we really have them widespread basically in use, and so also potential releases are widespread. There can be all sorts of different materials. Common ones are titanium dioxide nanoparticles, zinc oxide, silver. We can have organic-based carbon nanotubes and fullerenes, for example, and then we have also more specialized applications like quantum dots and things like that. And when we develop a new technology like this, that can theoretically bring a lot of benefits also for the environment. They can also be used in environmental, remediation applications and such, so they're not in itself bad. We still have to be, of course, aware that new properties can also mean new negative properties, so also new risks. And this is why, this is also where the motivation of my project comes from, to try and not wait 20 years until we see the particles everywhere and exhibiting negative effects in the environment, but to try and see proactively what are potential risks that could come along with these materials. And for that, just to look a bit at the bigger picture of risk assessment, that would also apply to any other material, basically. So of course, the first thing we always think about when we think about risk is what are possible negative effects on any kind of organisms. But that's not all we need to think about, because if you have a very high toxic effect but very low exposure concentration in the environment, your risk won't be that high. So it's really important to actually understand what are the concentrations that our organisms could be exposed to. And the straightforward thing would be to say, okay, we just go and measure it, but it's not that straightforward in the end, because at the moment there's almost no field measurements available for ENPs. They're very challenging to measure in the environment for all sorts of different reasons. So only slowly do we have methods that emerge that might potentially give us some actual data from the environment, but it will be a very long time until we actually have large-scale field studies and real data. And the other point is we actually don't necessarily want to wait until there's as much in the environment that we can actually measure it. And so we need to find other ways to get estimates of these concentrations. And we do have some information or some estimates on emissions. So there's groups focusing on emission estimates, and they do mass flow models where they look at how much is produced, how are these products then used and disposed of, and what are release rates in all these different stages of the life cycle. And we also have several groups that study the behavior of nanoparticles in the environment. So what are transformation processes under different conditions? They study this in the lab. Main processes that we're concerned with nanoparticles are aggregation processes, and in some cases dissolutions and surface transformations. But I will talk about these in more detail later when we talk about the actual processes in our models. And so basically we need a link to connect emissions and information on the behavior with information we have on the environment to then predict these concentrations. And for that we need environmental fate models. And we didn't have these for the nanoparticles when I started my project, so this is where the original motivation came from. As a background, let me walk you through a little bit of how these models work for organic chemicals, just so we can also understand which parts we can apply for nanoparticles and which ones we can't. So so we use in our group so-called multimedia mass balance models. There's all sorts of different types of environmental models you can use for different types of questions and applications. In our group we mainly focus on these multimedia mass balance models. The way that works is that you divide your environment into different compartments. So it could be air, soil, water, and sediment. This is like the simplest representation. You could always, depending on what specific location you're looking at, you could add, for example, a vegetation compartment, you could add snow and ice, you could divide water into fresh water and seawater, and you can also subdivide these compartments further if you want a more spatially resolved results in the end. So once we have our environment set up and described, we look at emissions either in one compartment or in several of these compartments. We then think about what are the transport processes, both within our model system between the different compartments and also transport out of our system. So we can have advective transport with air, for example, or water flow. We can have deposition process and resuspension processes between the different compartments. There's all sorts of ways the chemical can transport between all of these compartments. And then we also have to look at transformation processes. So for organic chemicals, classically this would be degradation rates, or for example interaction with aerosol particles, which can then again affect their transport behavior. Once we have all of these basically processes set up, we set up a mass balance for each of these compartments, where we look at how much chemical is coming in and how much is leaving the compartments through all of these transport and transformation processes. And we then have in these models, we normally, all of the processes, we describe them by first order processes, so it's a relatively simple system to solve from a mathematical point of view. So we just have a system of coupled first order differential equations that we can then use, we can then solve it either as a function of time or as steady state, depending on what we're looking at, and get then the concentration in each of these compartments from our chemical. So this is the basics of that. This can be applied to cities, it can be applied to, we also have global models that are based on this basic framework basically, and then of course the whole picture would look a little bit more complex than this. And for organic chemicals, the main input parameters, in addition to the description of the environment itself, so the input parameters that are specific to the chemical are relatively straightforward for the organic pollutants. So we use degradation half-lives in the different compartments, and we use equilibrium partition coefficient such as the octanol water partition coefficient, KOW for example, or KD, which is the soil water distribution coefficient. These coefficients, they are very powerful because they are relatively easy to measure, and they give a lot of information about the affinity of the chemical for different phases. So will a pollutant be rather transported through the water compartment or rather through the air compartment? So they can be used to parameterize a lot of these processes between the different compartments. So they're very powerful. This is where we are standing at with the organic chemicals. Instead, we use these type of models in all sorts of variation for many, many years. The question then was, okay, if we have this nice framework and we now want to use it and look at a new type of materials, the nanoparticles, can we just go ahead and use the same framework for nanoparticles, and can we use the same input parameters as we used for our previous chemicals? And of course, it's not as straightforward. We can just use the same model as it is, but we have to first take a step back and really think, what is actually the main difference between nanoparticles and organic chemicals, and how do these differences affect the processes that we have in these models and the transformation processes that they will undergo in the environment. An important thing to note here, and I mean it seems very simple and straightforward, but trust me, there's a lot of people who don't seem to see this so straight away. Nanoparticles and organic chemicals are not the same thing, so it's really something different type of materials, different type of chemicals. On one hand, you have single molecules where if you have one type of your whatever flame retardant, all of the active molecules in that bottle of flame retardant will be this flame retardant that you're looking at, right? If this is the pollutant you're concerned with. They are small, they can dissolve in different environmental phases, and that's why their behavior can be described with these partition coefficients, or a big part of their behavior can be described by that. Nanoparticles, on the other hand, are particles. They are solid particles. They're much larger than the molecules. Even if they are nano, they are still much, much larger. They are not present as just one type of particle, but you always have a distribution of different sizes of particles, so it's always heterogeneous, even if you try as much as possible to have them uniform. And they don't dissolve in the different phases in the environment. They are dispersed, so they can stay in a relatively stable, kinetically stable way for quite some time, but they're not actually dissolved. They still form separate phases, and you cannot describe their behavior with these partition coefficients, but you have to describe it kinetically. And there's there was a lot of debate, there still is, in the nano risk assessment field, which is a very interdisciplinary field. Also, people come from many different backgrounds. And you have a lot of people who still suggest that we should use these partition coefficients for nanoparticle risk assessment and as input in these fate models. And you have several people who actually also measured them and report them, although it actually from a fundamental theoretical point of view doesn't make any sense. And because we were quite frustrated with this, we ended up writing a perspective paper with a few other people in the field who were also getting more and more frustrated with that we recently published, where we wanted to go back and describe what are the fundamental physical differences between these different types of materials, and why you have to be careful when you choose to or when you make assumptions about what kind of fate descriptors you use. And in there we really described it in a bit more detail, and that's why I'm also going to do that here, so that's because I guess most of you have not actually spent that much time thinking about this question. So the reason that we cannot the reason that equilibrium partitioning is not applicable for nanoparticles, as I just said, you have on one hand the molecules that dissolve in the different phase and nanoparticles don't. But what does it actually mean? So, I mean, what does it mean when you if you were to try and measure this in the lab, right? So, if you look at the organic chemicals, if you wanted to derive any type of partition coefficient, you would take a two-phase system, maybe two immiscible liquid phases, or it could be a liquid and a solid phase. You would mix your chemical with this two-phase system. You wait some time for it to equilibrate, and then you measure your concentrations on each of these sites, and the ratio of this is your equilibrium partition coefficient. And the fact that this is at equilibrium, at dynamic equilibrium, means that it doesn't mean that they are static and that they all remain on one side. It just means that they are transferred between the two sides at the same rate. So overall, you always have the same ratio on both sides. And if you wait another half an hour, another hour, another 2 days, if you are at equilibrium, you will always have the same relative amounts on each side. So if you measure your partition coefficient 2 hours later, you should still get exactly the same value as a result, because it's equilibrium and it really describes inherently the system that you're looking at. If you now want to do the same thing with the nanoparticles, of course you can always go ahead and mix it in a two-phase system. That can always be done. What will happen is that they will not just distribute over to the other phase. They might, though, attach at the interface between the two phases. And then, of course, if you separate your two phases, you might still end up measuring something in one phase and something in the other phase. And then you can take the ratio and get some kind of value for it. It's always possible, of course, analytically, right? The problem is that if you don't think of what this actually means from the underlying processes, so if nothing is actually ever going back, it just means if you wait even longer, you will just have more stuff attached to the interface. But you don't, it's not a reversible process, it's not equilibrium. So if you measure your concentrations then, you will get a completely different coefficient. If you measure it, let's say, an hour later, or even maybe 20 minutes later, you will get something completely different. And if you think about it even a bit further, if you added new compounds to your system, in case of the dissolved organic chemicals, a new addition would disrupt your equilibrium, but if you wait a little bit, you would again have the molecules distribute in the same ratio on both sides, and you would again get exactly the same partition coefficient if you measured the concentrations then. Whereas for the nanoparticles, you wouldn't. You add more, you have even more that attaches, and in the end, you just have an even different concentration ratio. And what I'm trying to show here is that really whatever coefficient you measure here, you can measure it in the lab. It's not that you can't measure it, but it just doesn't have any meaning. It doesn't describe the system in the way that you describe the organic chemicals here. So if now you were to use one of these as a fundamental input in your fate model, you can imagine that for this system, if you use this one, or this one, or this one, you will get completely different predictions in your fate model. And this is why this is so dangerous to propose these as input parameters in your model, because they really have no meaning, and they can really affect the predicted distribution in a very, very strong manner. Alright, so if we are now in this room, all on the same page on this one, we can look a bit further at our original question. So what do we actually have to do then if we want to go from here to fate models that are actually applicable for the nanoparticles? So as you might have guessed, we cannot just take it as is. We do have to make some modifications to account for the properties of the nanoparticles, right? And here I started my PhD, and I'm doing the whole time of PhD focused on the water compartment. That's why it's a bit enlarged here. The main reason for that choice was that most emissions were predicted to go to the water compartment through sewage treatment effluents, and also most studies on behavior when I started my thesis were on the water compartment, so this was the one to start with. We now do also have other people looking at other compartments. We have one project that's currently looking at how to look at soil transfer, for example. Just a whole lot of other problems that I won't go into today. What I did then was to look at, in a surface water sediment system, what are the relevant processes in such a fate model for organic chemicals on this side here, and what are corresponding processes for nanoparticles, and how can we describe them then also really mathematically to use them as input in our fate models. We have three kind of groups of processes. On one hand we have transformation and degradation processes, then we have interaction with naturally occurring suspended particulate matter, which also affects then the further transport of the particles or chemicals, and we have all sorts of transport processes that are strongly affected by the environment that you're actually looking at. I will now go in a bit more detail in each of these. So for transformation or degradation, for organic chemicals, like I said before, we basically just look at the half-life of the chemicals in the different compartments, get a degradation rate, and in the easiest case, we will have full degradation of the chemicals. for the organic chemicals, I'm showing you the simple case here. Of course, they can also be transformation degradation products that you don't have to look at more for the organic chemicals as well, but we won't focus on that today. For the nanoparticles, in most cases, or in almost all cases, you won't have complete degradation. That's not something we really assume will happen so easily, but we can have all sorts of transformation processes happening. So the particles can aggregate with each other, which will change their size and also their properties. Some nanoparticles can dissolve. Nanosilver, for example, can dissolve in the environment, and some nanoparticles can undergo all sorts of different types of transformation on their surfaces. And this is important because the transformation products here will have very different properties, both in terms also of their hazard, so the toxicity can be affected, both in positive or negative direction, of course, and also their transport and interaction with other surfaces in the environment will be affected by their surface properties and their transformation. So it's important to understand that even if they don't completely degrade here, like here. An important process is the interaction of a pollutant with in the water column with naturally occurring suspended particulate matter. So suspended particulate matter, we mean all sorts of non-dissolved natural compounds. They could be all sorts of colloids, clays that are present in the water column and that can interact with our pollutant and thereby affect their transport processes. So if you have a pollutant attached to suspended sediment particle, it can sediment down with that towards the sediment compartment much faster than if it was freely transported in the water column. So this is why this is an important process both for organic chemicals as well as for the nanoparticles. And here, this is one case where the equilibrium partition coefficient is very important for the organic chemicals. So we have this KD, the soil water partition coefficient, which describes the proportion of our chemical that will be in the water column and the proportion that will be attached to the suspended particle. And this is, because it's such an important process, this is also where the use of using partition coefficients for nanoparticles was always kind of strongly suggested. But like I said before, this is not something we can describe in this manner, so we have to look at it in a different way. We have to see that both the nanoparticles and the natural particles are all particles that move around in the water column and can collide with each other, and then depending on their relative affinities can either attach or not. That will depend on many properties of the particles and of the medium. And so we describe this as this heteroaggregation process, and we have on one side the collision rate that we can calculate based on the physical properties of our respective particles and our medium. And then one important parameter here is this attachment efficiency alpha, which basically gives us an indication on it's a probability of how likely a collision will result in attachment. So if alpha is 1, all collisions are expected to result in attachment, and if alpha is much lower than 1, then we have a lower successful attachment rate, basically. And alpha is complex because it depends both on the properties of your nanoparticles, of your natural particles, and also of the properties of the medium, because those will again affect the surface properties of your colliding particles. So it's not something that we can just say for each nanoparticle there's 1 alpha. In the way where for the organic chemicals there would be for every chemical there's only 1 octanol water partition coefficient. So this was also one reason that people wanted so much to use these kind of simple fate descriptors, right? Yeah, so this is quite a tricky parameter to obtain for these models. And then we have all sorts of transport processes. We can have, as I just said before, sedimentation. Once the pollutant is attached to the SPM, it can sediment down. We have advective transport through water flow and sediment transport. And for the organic chemicals, we can have diffusion processes between water and air, and also between water and sediment that can affect the transport. And for the nanoparticles, many of these are similar. So, I mean, the advective flow acts as much on a dissolved chemical as it does on a nanoparticle. We have also the sedimentation here with the SPM. We can additionally also have sedimentation of the nanoparticles themselves. If they are big enough, they might also sediment due to gravitation. And what we don't have are these diffusion processes here, because those again work only for the small dissolved chemicals and are also often described with these partition coefficients amongst other things. Alright, so this is basically the framework that I spent the first part of my PhD developing on. So I did a lot of literature research and talked to a lot of people to get to this point and to say this is what we suggest a useful framework to model nanoparticles in the environment. And then we applied this framework to start with to a case study of titanium dioxide nanoparticles in the Rhine River. So we converted basically this original 4-box model I showed you to a model that describes actually a specific river. So to do that, we basically attach, in our case, over 500 boxes, one after the other, to really be able to simulate this horizontal flow. And each of these boxes is further subdivided then into 3 compartments. We have a moving water, a stagnant water, and a sediment compartment. This was just the first case study, so we didn't assume realistic emissions all along the river. We just emitted nanoparticles once here in what corresponds to Basel in Switzerland. The data from here comes from a study from Friedrich Gottschalk, who did this mass flow models where they, what I mentioned at the beginning, where they to predict emissions, so how much is emitted through the life cycle of the nanoparticles into sewage treatment and comes out then as effluent. So this is where this data comes from. And then we wanted to, we parameterized from the whole list of processes I showed you before. We selected the ones that are relevant for our given system. So because the nanoparticles with titanium dioxide, for example, we didn't have dissolution as a process. If we were to look at silver, we would include, we could include that as a process. And so these here are the main processes that we looked at in this model. The central one is this heteroaggregation. So again, this is the one, because while we could assume that some homoaggregation, so aggregation of nanoparticles with each other, also occurs, this is actually occurs to a much lower extent, because the nanoparticles at the current state, they don't reach the environment in such big amounts. So we have quite low concentrations. So compared to the concentrations of the natural particles, the nanoparticles are much more likely to aggregate with natural particles than with each other, which is why we focus on the heteroaggregation here as the central process. And then here we have all sorts of water exchange processes, sedimentation, and advective transfer processes that are specific to this given river. So when we set up this, we ran into a problem because we can calculate the collision rate, but we were not able to predict the attachment efficiencies, because it depends on so many different factors, properties of the nanoparticles or the natural particles of our system, that we're not able to predict it in any way. And so what we did is that we used this case study as a first test of whether or not this process is actually important. This is one of the nice things about these kind of models, that you can use them to assess the interplay of all these different processes in an actual realistic scenario, to see whether the process that you think is important is actually as important as you think. Because it could be that the particles, for example, I don't know, are transported much faster down to the sediment before they even have a chance to heteroaggregate, or that your water transport velocity is so much faster than anything else that all the other processes are much less important. And so we did this, and we did see that the heteroaggregation and specifically also this attachment efficiency are important parameters. We saw that if we have a high attachment efficiency, we have a very fast removal from after the emission source. So the nanoparticles very quickly heteroaggregate and sediment down to the sediment. And when we had a very low attachment efficiency, we saw that even 700 kilometers away from our emission source, we still had particles present in our water column. So we realized that this is actually an important process, but as I said before, there was actually no data available on this process. So what I did was to talk with a lot of people in the field, and we set up a collaboration with Jérôme Labille and Jean-Yves Botero, who work at the CEREJ in France. And they study a lot of nanoparticle behavior. And so with them, we developed a method to actually measure this heteroaggregation and obtain these attachment efficiencies in the lab. So we recently published this. I won't talk about this in more detail because I thought today I'd focus on the modeling part, but just so that you're aware, this is something we actually had to do because we couldn't actually go further with our modeling at that point. And we needed this to do the last part of our modeling part, which I will talk about briefly now. So the last part of my project, we then decided to look at a more large-scale model and a bit more realistic than just this one river, where again, even our emissions were not very realistic because we just had one emission source. So we decided to look at the whole network of Swiss rivers that are attached to sewage treatment plants, and then we obtained emission estimates for each of these sewage treatment plants in the collaboration with Father Gottschalk and Bernd Nowak and ENPA, who are the ones who were doing these mass flow models that I also used as input for my previous model. So they gave me then specific inputs for each of these sewage treatment plants, and I combined this with the river model that I developed before. So I adjusted this river model to each of these river sections and made it a big network where each river received input from either a sewage treatment plant or from a previous river section, or more, sometimes two river sections and one sewage treatment plant, in any combination that you wanted. Then we needed, of course, to also parameterize these river sections to be able to set up the model specifically for all the different parts of the river, and for that we got quite a lot of data from the Swiss Federal Institute of the Environment. They've been doing long-term monitoring of all sorts of water quality parameters and also discharge and things like that, so that was very useful. And so we mapped then discharge to get then information on the water flow for all of the rivers, and we wanted to get an estimate of these attachment efficiencies in the different river sections. Again, this is not perfect, because the perfect thing would be to go to each river section and know exactly what natural particles are in there and to measure the attachment efficiency for each of them individually. That's not possible, as you can imagine, but we wanted to get an idea, is it rather high attachment or low attachment that's already bringing us a lot of improvement compared to the previous study that we had. And the main water parameters that influence this attachment efficiency we found during our experiments were the concentration of calcium in the water, which higher calcium concentration increases aggregation, so leads to higher attachment efficiencies, and dissolved organic carbon, which gives an indication of how much dissolved natural organic matter is present in the water, which then in turn actually stabilizes the system against aggregation, because it can absorb on the surface of the nanoparticle and then give a steric and electrostatic stabilization. And so based on this information, we estimated then the attachment efficiencies for each of these different sections. We did this for different scenarios. This is a scenario in January, where we have quite low discharge. We also did this for another scenario in June, and in theory we could also do this for every month, because the data was also available at a high temporal resolution. That was very nice. And here I'll just quickly show you the results for concentration of the titanium dioxide nanoparticles in the water column in the low discharge scenario in January. So the dots, these are all the sewage treatment plants. And the size of the dots reflects the number of inhabitants that are connected to this sewage treatment plant. So here you see some very large, this is Zurich, for example, this is Basel, Geneva. And so it's not too surprising that we often have very high concentrations close to emission sources where there's a big population attached to. Other things that we saw that I don't show here is that we had much higher concentrations overall in the sediment in all cases. This is also something we saw in the previous study of the Rhine River. So the sediment in all cases will always be the sink of the nanoparticles. So that's very important. The attachment efficiency mainly will lead to a longer or shorter residence time of the particles in the water column, but it won't affect that overall you will always have the highest concentration in the sediment. This is in every case, this is what we saw. And we didn't see much transport through the water column, because we had fast heterogation and sedimentation in most cases, but we did see quite some transport then of the particles through the sediment compartment. So we saw higher concentrations even a bit further away from the emission sources. And one thing that this, for example, is shows why such studies are also important is that the fact that we expect many more nanoparticles in the sediment compared to the water compartment also can favor or can give indications of where risk assessment should maybe focus on. So rather than study maybe toxicity for aquatic organisms, maybe it would be good to focus more the studies on what effects do nanoparticles have on sediment organisms, for example. So this is the kind of things where a model can also give support, in addition to what I previously said about the prioritization of which processes to study on experimentally. And we also looked at zinc oxide and silver nanoparticles. This is just it's the same results as written differently. I have it's the total number of kilometers that have the concentration in a certain concentration range. So here we have a low concentration, and the right is a higher concentration. And we see that overall the titanium dioxide nanoparticles are always present in the highest concentration, zinc oxide second highest, and for the silver nanoparticles we actually never saw particle concentrations in not even a nanogram per liter range. It was always much below. So this is due to just lower emissions of them as well, right? So this is important to think of if you want to develop methods to detect these in the environment. If you want to try to detect silver, you're going to have a much harder time than trying to maybe detect titanium dioxide, which is at least present a couple of orders of magnitude higher than the silver. Yeah, so that's that, and just maybe to look back to the end of my talk at the original part. So really what the main focus of my work was to look in this whole bigger picture of risk assessment of nanoparticles was in this development of the fate models. And I want to emphasize one more time, because this is such a source of so much discussion during this time. We really need to use the right descriptors for these models. I mean, the models are not perfect. We need much more information on the actual processes, on the process for a given condition, but as long as we use the appropriate descriptions of this, as soon as we have better information, we can always improve our model predictions. But if you start off in a completely wrong direction, then whatever you do, you will always predict something that really doesn't make much sense. So this is really the idea of that. And just the last point is that we also want to emphasize that fate models, we believe, can be really useful as a tool to address situations like this. In the nanoparticle risk assessment at the beginning, everybody kept saying how complex it is. We have so many different particles, so many different environmental conditions, so many types of applications, and some people were like, oh my god, we can never ever assess this in any useful way. And the nice thing about the models is that they can be used to try and give a bit of a structure in this field, to combine knowledge that we obtain through all sorts of different lab studies. We can use them to run different scenarios, and we can use them to prioritize research efforts on certain types of processes or certain types of, for example, organisms to study toxicity tests. So we try in our group, although we do almost no lab work ourselves, to work a lot with people who actually do work on these things, because I think only if we do it together we can get anywhere. I think if the modelers and the lab scientists all stay in their own little corners, we won't really get very far, especially in a field like this one. It's still quite fresh and a bit, let's say, I think we're still learning a lot in that field. Alright, with that I come to the end. Thank you for your attention, and acknowledge all my collaborators and co-authors. Because it was really a very collaborative project that I did. It was very nice. Yeah, thanks.
Okay, are there any questions for Antonia?
Can you go back 2 to 3 slides? One more. That's the one. It's interesting because if your model is saying actually the concentrations of silver nanoparticles are going to be much lower than zinc or titanium dioxide. But you say that they're open to the dissolution process, but also they can hang around. And although your model shows that there's low concentrations, but if they are able to stay maybe in the sort of benthic compartment and start to build up, and they maintain their antimicrobial properties, your models, if you don't talk to toxicologists and other people, the models sort of almost suggest that it's not a problem. And so to sort of emphasize the comment that you made at the end, that the modelers really need to be speaking to everyone else.
Yeah.
Otherwise it looks as if there's no problem there, but actually there may well be something
that's true.
Yeah.
And also if we wanted to, we could model this much more explicitly, right? We could also say, okay, if we are worried that around a certain sewage treatment plant there might be a lot of silver emissions, maybe because it's close to a hospital and they're using it in a lot of antibacterial applications, because here we didn't, the emissions are just based on populations, you could make this much more specific. So you could also make your model for a much smaller scale and include this whole transformation process in there to see what is the amount that is present as an actual silver nanoparticle, what is dissolved silver, and then often the dissolved silver actually forms silver sulfide in the environment. So this is why most people actually think it's probably not so much of a problem, not just because of low concentration, but for other reasons. But this is something we could actually look at in more detail. Yes, that's right.
Charlie?
My question follows on quite nicely from that, and I'm not a scientist at all, and I really enjoyed your presentation. I thought it was incredibly clear, so thank you. There's a non-scientist in the audience. My question is about, I understand all the co-reactive attached using the models, but how do you see the application, and how do you see that linking to the end part of the process about risk assessment? What are the wider repercussions of what you've done with this model?
I mean, one big problem, I guess, in the nano community is that people, when they were trying to do risk assessment in terms of the toxicity tests, the people were trying to do toxicity tests at much too high concentrations. So I think one thing that we show with the models, and there's different other people who've done different types of models, we all come to similar order of magnitude concentration ranges that are very low until now still, right? And most toxicologists, they are trying to pump their system full of nanoparticles and just so that they can see an effect, but these are not realistic exposure conditions, right? So I think this is one thing that we would emphasize here strongly, that people would have to adjust their test maybe to rather do long-term chronic exposure tests at lower concentrations rather than try to force these high concentrations into their systems, which leads to a lot of other problems because the particles are not stable. And I mean, there's people who try, I've seen talks where people basically said, oh, we ended up having a problem in our toxicity test because we put so much nanoparticles inside that our algae didn't get enough light, and then they died because of that. But I mean, this is not, this won't be the concentration we will see in the environment. This is completely unrealistic, so we don't even have to look at that. I mean, and also not in the next 10 years we won't get this, whatever, because we can also do future predictions with that, right? With all sorts of scenarios in how the usage will change, and we still never get to these high concentrations. So it's a lot in that direction as well. And also to look at one thing with the nanoparticles, I think, is that due to this kinetic nature they have, we would rather have to look at local hotspot concentrations. So if we're in areas where we have high populations, or we have some industry that looks at that produces nanoparticles, and we look there, can we be concerned with high concentrations there? They won't distribute in the same way around the globe as, for example, volatile organic compounds did, right? So it's a bit of a different approach, maybe also, to not always have these large scale models where we have very average concentrations, but to look a bit more locally and identify hotspots, and then try to see if we can adjust our regulation there, maybe. So it's a bit in these directions, I would say.
Yeah.
So when we risk assess a normal chemical, we get our exposure concentration and our effects concentration, we divide by a big safety factor. How do you think we should do it for nanoparticles?
I think it's very complex, because I think the problem is that we don't have these, we don't have the same dose response curves as we have for the organic chemicals. In some cases, you see that if you increase the concentration, you have actually lower toxicity effects because the particles start aggregating with each other. This is what they see in the tests. So you can't always just say higher concentration is worse. Sometimes lower concentration is worse. So I think we just have to realize that it's a different approach to risk assessment. I think one problem is that people have tried to really force these established methods of risk assessment on the nanoparticles, and that's created a lot of confusion. A lot of people try to use these standard OECD tests, for example, in terms of to study the behavior and also the toxicity of the nanoparticles, and they realize that it doesn't work. But I don't find it so surprising, because when we did the risk assessment with the chemicals, we first tried to understand how the chemicals work and what potential negative effects they have, how they behave, and then we create our risk assessment framework around it. And for nanoparticles, maybe we also have to be a bit more patient and try to get a better understanding of our system before we think of the appropriate measures. We can't necessarily force the old ones on it just because we have to do it right now. I think it creates more confusion than it really helps. This is my impression.
Yeah, so picking up on that then. So you sort of, I mean, I agree with the partition coefficients not working and stuff, but you sort of, I guess you sort of indicated that they work well for organic molecules. I guess the question is that really true?
They work
I
well.
would argue perhaps we should be moving more towards the kinetic approach for some organic molecules as well.
I mean, didn't touch upon this here, but we mentioned this also in this KD, in this partitioning paper. Of course, the partitioning coefficients work well for ideal organic chemicals, for small chemicals that really dissolve in the environment, that are not charged. So we have a lot of organic chemicals that where it already doesn't work, and people are, I guess, more or less aware of it. I mean, there's a lot of people who are aware of it and who point that out, that for a lot of the pharmaceuticals also that you study, it probably doesn't really work in many cases. You have large molecules that start to behave more than particles than like chemicals, and you have all the charged molecules where you run into a lot of trouble as well. So this is exactly the point. It already doesn't work well for many of the organic chemicals. And we still have, this was actually an argument we received when we submitted this prospectus paper, that people said, but it's already not perfect for the organic chemicals and we're still using it, so then we can also use it for the nanoparticles. And we said, but you can't argue saying that one thing is wrongly applied in one case, we can wrongly apply it in a case where it's even less appropriate, right? So, yeah. But there's a problem. The people who started to study the nanoparticles, they were actually often not aware of these limitations for the organic chemicals. They just saw that this is how it was done, and they were not in the discussion, right? In our group, we look mainly at non-charged and quite volatile compounds where it works well, but we are aware of the ones where it doesn't work. And I think you know better than me of all the other kind of approaches you can use to try and overcome this. But people are aware in that field that it's not perfect and that people are looking for other approaches. But the nano community was not, so they tried to kind of go back to these methods.
And one last question. So, in the spatial modelling, you seem to have missed the wastewater treatment. I mean, is it possible that actually the water chemistry doesn't matter? It's what happens in the wastewater treatment works that drives that? Yeah,
it's possible. Completely. This is something that we still don't know enough about yet. So we took the estimates that we got from this study from the people from ENPs, who give us estimates for what comes out of the effluent, but they don't assume any kind of transformation in the sewage treatment plant directly. They just assume that a certain amount will be removed, right? So they don't, but they don't look at what actually happens. So for example, the silver, there's people who look at the transformations of silver in sewage treatment plants in much more detail, and what they see, for example, is that normally it's actually not silver that comes out. If anything comes out, it's already silver sulfide. So this is something that we should take into account better, but unfortunately we actually don't have so much information on. These are the people who look at that, but then what happens to other nanoparticles, what happens to the coatings on the particles? I mean, there's still a lot of open questions for sure that we also don't answer here in our studies. Yeah.
Because following on from what Alistair just said about the sewage treatment plant, that is your hotspot, isn't it?
But this is where it comes out of, yeah.
Yeah.
Unfortunately, we don't know how it comes out.
Actually, that really probably is the most important thing for everybody to be studied.
Yeah.
Not necessarily the river loading, but the sewage, because if you knock a sewage plant out with your super antimicrobial silver or whatever it is that they produce, that's the most important hotspot in our modern society.
Yeah, I agree.
No sewage or another.
And a lot of this is exactly, it's also a problem. We don't understand enough in what form the particles actually come out of this whole technological compartment, basically. Both out of the sewage treatment plant, also what happens before. I mean, there's a lot of things that can happen already in the product. It's quite it's not so straightforward. That's why it's not just titanium dioxide, and then we can whatever titanium dioxide in a product comes out the same way out of the sewage treatment plant. No, if titanium dioxide out of the sunscreen will come out differently. There's titanium dioxide out of the paint. It's a complex question to answer for sure. And so that's why also the model predictions we do, I mean, I see it more as a tool that we can use to understand our system better and to get rough estimates, but I would never say this is exactly the concentration you're going to get in your surface water at this point. I think we are still far from that. Hopefully, we might get there one day, but I think we're not there yet. But just one more thing, in this type of modeling framework that we made, we can also follow different types in parallel, right? So we could also have a nanoparticle. We can look at titanium dioxide with a coating. We can assess the transformation rate of the coating, and then have another titanium dioxide species run at the same time in the model with different properties and different behaviors. So this is possible in this model. We did it with for some student projects, but we don't have really real data to actually justify it yet for publication. But it's something that this model framework allows you to do. So that's another nice thing. Yeah.
When you were talking about calculating your attachment efficiencies of your particles to your carbon and your particles to each other, it sounded like you assumed particles, once they're stuck to each other, are stuck to the carbon or whatever, if they stay stuck to it. Do you have any data that demonstrates that is the case?
No, but people start to look in that in more detail, right? So this is, I mean, in most cases we don't assume that it will be detaching so easy, because it's often reaches quite a deep energy minimum and wouldn't disaggregate. So we don't assume this is the dominant thing to happen, but I think people are only slowly starting to look at this as a process, how changing dramatically the conditions might affect the interaction, might lead to disaggregation, or even if you have high energy input, you could also disaggregate your particles. So this is something we don't model explicitly here, but we are thinking of how to do that in the future. Because it could be relevant. You could have something that gets attached to something, gets transported really far, and then suddenly gets released again because of a disaggregation process. So in theory it's possible.
Okay, any more questions? Okay, well, thank Antonia again. Thank you very much. Okay, is there a plan for later?
I think the plan's to go to the pub, isn't it?
That's always your plan, yes.
So yeah, I think we were thinking of going into town and getting a drink. Where should we go? The usual?
I don't know if there's going to be enough
Sorry?
space. There's always a space issue with
Yeah.
usual.
Should we go somewhere else a little bit